title of my talk today is Quantum Simulation with Ultracold Atoms in an Optical Lattice. Okay, so this is the outline of my talk today. First, I would like to make a brief introduction of a quantum simulation of a Fermi Hubbard model with a special emphasis on the quantum magnetism of Fermi Hubbard model using alkaline atoms. And next, I would like to talk about our recent work on a quantum simulator of SUN Fermi Hubbard model. And next, I would like to also talk about our recent work on a two-orbital quantum simulator. And finally, I will summarize my talk. Okay, and the first part of my talk is a brief introduction of the quantum simulation of Fermi Hubbard model. The Fermi Hubbard Hamiltonian is written like this. And first term describes the hopping between adjacent lattice sites and characterized by the hopping energy T. And the second term describes the on-site interaction when the two particles occupy the same lattice site and is characterized by the on-site interaction energy U. And this Hubbard model is very important in condensed matter physics because it describes the novel quantum magnetism and unconventional superconductivity such as a high TC cuprate. And for this problem, various numerical simulation methods are developed like this. And some methods are useful for some particular problem of Fermi Hubbard model, but in general, they are not powerful enough for the study of a Fermi Hubbard model. Therefore, quantum simulation approach of Fermi Hubbard model is very important. And now the atomic physicists can prepare ultra-cold Fermi gas with a temperature much below the Fermi temperature. And by loading this ultra-cold Fermi gas into an optical lattice, we can successfully implement the Fermi Hubbard model by using the ultra-cold Fermi gas in an optical lattice. And one of the goals of such a quantum simulation research of the Fermi Hubbard model is to get a deeper insight on the behavior of the strongly correlated electron systems such as the high TC cuprate. Here I show the schematic phase diagram of the high TC cuprate here. Even now, it is not well understood after almost 30 years of the first discovery of the high TC cuprate. Okay? And now the state of the art of quantum simulation research of the Fermi Hubbard model using the ultracold atoms in optical lattice can reveal the quantum magnetism of Fermi Hubbard model. The experiments are done by using two-component fermions of lithium-6 or potassium-40 of alkaline atoms. And yeah, the ETH group was the first to study the short-range magnetism of a Fermi Hubbard model, like this. And the Rice group was the first to successfully observe the antiferromagnetic spin correlation of the fermions in an isotropic cubic optical lattice in a 3D lattice configuration by a technique of optical Bragg scattering technique. And MIT group, Harvard group, Max Planck group, and also recently the Princeton group used the powerful technique of quantum gas microscopy to create and study the quantum magnetism or spin correlation of the fermions in optical lattice. This quantum gas microscope technique is a really powerful technique. And by using high numerical aperture objective lens close to the quantum gas in optical lattice, one can achieve the very high sensitive detection of the single atoms with high spatial resolution. And one can one can achieve the site-reserved imaging of a single atoms in optical lattice like this. And in addition to the detection of the single atoms, one can also manipulate and control the single site by using this optical setup. So with this technique, one can prepare almost arbitrary atom distribution with this technique like this. Yeah. And the quantum gas microscope technique was first demonstrated for the bosons in optical lattice, namely Bose-Hubbard model. And important phenomenon of the Bose-Hubbard model is the superfluid multi-insulator transition. And at the small u over t, we expect the formation of the superfluid state of the atoms in optical lattice. And at large u over t, the interaction plays an important role to localize the atoms due to the repulsive interaction. And so such a state is called the multi-insulator state. And previously, the superfluid multi-insulator transition was studied with the technique of time of flight by releasing the atoms in optical lattice suddenly and measure the atom distribution after some free expansion of time. Therefore, the observed atom distribution reflects the momentum distribution in optical lattice, atoms in optical lattice. Here, I show the obtained time of flight images. And clear matter wave interference pattern is a signature of the existence of the superfluidity of the system. And absence of the interference pattern is a signature of the formation of the multi-insulator state. Each atom is localized, so no phase coherence exists in the multi-insulator state. With this behavior, we imagine that the atom distribution in optical lattice should be like that in a superfluid state and should be like that in a multi-insulator state. Yeah, this is a previous method, but with the quantum gas microscope technique, one can directly measure the atom distribution in optical lattice in a superfluid state and multi-insulator state and for the in between like this. So this is a really direct and powerful technique. And more recently, this technique was applied to many interesting physics, such as the many-body localization in two-dimensional optical lattice. This was the work by Max Planck group, and they studied the localization and thermalization and non-thermalization behavior with this technique by creating the disorder potential by using the spatial light modulator. Okay, and more recently, the quantum gas microscope was also developed for Fermi Hubbard model. And Hubbard group successfully created and observed antiferromagnet with this system. In this experiment, they produced the deformed optical potential by using the DMD technique. And then they obtained a very low temperature of the atoms in optical lattice, only about 1/4 of the hopping energy. So at this low temperature, they can achieve antiferromagnet like this. And more recently, they also study the string patterns of a doped Fermi Hubbard model. And they provide the important experimental benchmarks for the many sophisticated theoretical calculations. Yeah. And yeah, all of these works are very great achievement and very important. And yeah, but in our approach, we are working with the two-electron atoms. And so we can study the Fermi Hubbard model, but with more enlarged spin symmetry of SUN spin symmetry by using the nuclear spin degrees of freedom of two-electron atoms. Nuclear spin degrees of freedom are decoupled from the electron angular momentum in the ground state singlet S0 or metastable state of a triple P0. J equals 0 in these states. So yeah, with this system, we can study the more exotic Fermi Hubbard model. Yeah. Okay. Now I'd like to talk about our recent work on a quantum simulator of SUN Fermi Hubbard model. Okay. With SUN Fermi Hubbard model with n spin component, we can study novel SUN magnetism. Okay. In the case of SU2, in a square lattice with a half filling, such an antiferromagnet is theoretically predicted and experimentally observed. So this is rather well established. But in the case of SUN, in a square lattice with 1 over n filling, namely one atom in one optical lattice site, then such a novel quantum magnetic phases are predicted to occur. And in addition, upon doping, the D-wave superconductivity or superfluidity is theoretically expected for the case of SU2. But in the case of SUN, there is no works for emergent superfluidity or superconductivity, yeah, for the case of SUN. So this is interesting new direction of a research of a Fermi Hubbard model. Yeah. Okay, and experimentally, we successfully implement the SU6 Fermi Hubbard model by working with the ytterbium 173, which has a nuclear spin 5 Hz and repulsive interaction with this scattering length. And SU6 Fermi Hubbard model can be written like this. And here you can see that the on-site interaction is nuclear spin independent, which assure the SU6 symmetry of this system. Okay, using this system, previously we successfully demonstrate the formation of SU6 multi-insulator state like this. And interestingly, the lower temperature is achieved in a system of SU6 than in SU2. In other words, Mott plateau is more easily developed for the case of SU6 than for SU2. Okay? This can be understood as an effect of the Pomeranch cooling in charge degrees of freedom. Pomeranch cooling effect was the important cooling method for realizing the first superfluid helium-3 by Yoshiro, Lee, and Richardson. But now the Pomeranch returns to cold atom system as a novel cooling method for the atoms in optical lattice. Okay. And this Pomeranch cooling effect of an atomic gas can be understood by considering the entropy versus temperature diagram. Okay, let me explain. Before loading to the optical lattice, the atoms are prepared in a harmonic trap. Then the system can be considered as the ideal Fermi gas. And so the entropy is written like this. So we have a linear relation between the entropy per particle and temperature of the atoms. When the atoms are loaded into optical lattice, then each atom can take spin up or down. So it can carry the entropy of log 2 here. So entropy versus temperature curve becomes something like this. Okay? And in the case of SU6, each atom localized in optical lattice can take any value of 6. So it can carry large entropy of log 6. Yeah, so entropy versus temperature diagram becomes like this. So when we start from this initial temperature in a harmonic trap, and by adiabatic loading from the harmonic trap to optical lattice, then we obtain the atomic temperature for the case of SU2. Because this is the adiabatic loading process, so entropy is constant during the lattice loading. And in the case of SU6, we have a temperature here. So this is the Pomeranch cooling effect, which was observed in our previous experiment. Yeah. And but here there is no spin correlation, and if we start with a little bit lower temperature, then we can reach the spin regime of a spin correlation or quantum magnetism of this system, SUN Fermi Hubbard system. Since the log 6 is about 1.8, so from this relation, if we could prepare the atomic ensemble in a harmonic trap with a temperature of about 18% of the Fermi temperature, then we could reach the regime of a quantum magnetism. Now we can prepare such a low temperature Fermi gas with our technique. Okay, and so we can study the novel SU and quantum magnetism with our system. Okay, this is a Pomeranch cooling effect of atom gas. Okay, our method for measuring spin correlation is based on the technique developed by ETH group for SU2 system. Let me explain this method. Suppose we have some spin correlation between the neighboring site in optical lattice, like this. To detect this spin correlation, we first freeze the intersite hopping by increasing the optical lattice potential depth, like this. And then we perform a STO, singlet triplet oscillation, by applying a spin-dependent potential gradient. Okay, and in the presence of the spin-dependent potential gradient, we can introduce the extra phase factor here in the wave function. Then, initially prepared spin singlet state can be converted to the spin triplet state after some time. And initially prepared spin triplet state is transformed to the spin singlet state. That is why this is called a singlet triplet oscillation. Okay? And we are working with the nuclear spin degrees of freedom. So usual magnetic field gradient is not large enough. So we, in our experiment, we generate spin-dependent potential gradient by off-resonant laser beam with intensity gradient. Okay, this is an explanation of such a nuclear spin-dependent potential gradient. For the system of SU2, we apply a circularly polarized laser beam with the intensity gradient like this. And the energy spectrum becomes like this as a result of AC Stark shift. Yeah. Because of the circular polarization of this light, the light shift becomes nuclear spin dependent. So it mimics the Zeeman effect due to magnetic field. Yeah. And we consider the spin 5 Hz and spin minus 5 Hz as a SU2 system among these 6 energy levels. Yeah. But in the case of SU4, instead we apply a linearly polarized laser beam. Yeah. I didn't say about this resonance. These resonance correspond to the optical resonances in this singlet SL to the P1 transition and split by hyperfine structure. Yeah. We our laser beam is set at this detuning. Yeah? And in the case of SU4, we apply a linearly polarized laser light. And then SC Stark shift results in this energy diagram, energy levels. Yeah? And we take these 4 spin system as a SU4 spin system. And in the case of SU6, we take all of these 3 energy levels as a SU6 system. I will come back later to the case of SU6. Okay? And after we perform the STO process, we merge these 2 sites into a single site. If the spin singlet state is formed, then 2 atoms occupy the same vibrational state in a merged single site. Then these 2 atoms can be converted to the molecule by the application of the photoassociation laser beam. And eventually, they escape from the trap. And in the case of a triplet state, they are not converted to the molecule and no atom loss. Okay? In this way, we could detect the spin correlation as an atom loss. Yeah, this is our method. Okay, this is a typical example of our observation of the singlet triplet oscillation of SU4 fermions. Yeah. We performed the measurement in a strongly dimerized lattice with this Hubbard parameters, and to artificially induce the spin correlation within the dimer. With the large tunneling energy, TD, corresponding exchange energy becomes large. So we expect the formation of the spin correlation. Yeah. And here you can clearly see the oscillatory behavior of the signal. And in a separate measurement, we could determine the total atom number here at this value. So this atom loss corresponds to the initially prepared spin singlet state. And this atom loss, after half of the cycle of the STO process, is contributed by the initially prepared spin triplet state. Yeah. From this behavior, we could deduce the important quantity of the normalized STO amplitude defined like this. And this quantity is related to the transverse spin correlator in the system. Okay? And observed normalized STO amplitude is plotted for various initial entropy per particle, both for the SU4 and SU2 cases, like this. And you can clearly see that larger STO amplitude is observed in the system of SU4 than in SU2. And from these signal amplitude, we can determine the temperature of the atoms like this. Yeah. We determine this temperature from the theoretical analysis based on the atomic limit approximation. Yeah. And again, you can clearly see that the lower temperature is achieved in the system SU4 than in SU2 for various entropy per particle. And this can be considered as a result of the Pomeranz cooling effect, but now on quantum magnetism in a dimerized lattice. Yeah. In the case of SU2, we have only one possibility of a spin singlet state, spin up and down. But in the case of SU4, we have 6 different pairs for singlet state formation. So it can carry, again, the large entropy. So Pomeranz cooling effect works, even for the quantum magnetism in a dimerized lattice. Okay. Okay. We next turn to the study of the quantum magnetism of SU6 Fermi gas. The number of 6 is the largest achievable in our system using the ytterbium 173. And again, the experiment was first done with a strongly dimerized lattice to induce the large spin correlation artificially within the dimer. And the temperature is almost 0.1 in this measurement. And you can clearly observe you can clearly see the oscillatory behavior of the STO signal. But this is not a simple cosine function, as in the case of SU4. But this is because there are many spin pairs which contribute to the STO signal with different frequency of omega, 2 omega, and 3 omega. Therefore, expected STO signal can be written like this, which consists of the frequency component of omega, 2 omega, 3 omega. And actually, the observed signal is well fitted with this function. Okay? And next, we study the quantum magnetism of SU6 in isotropic lattice configuration, which is more interesting rather than dimerized lattice. Okay? Now, this is a case of a 1D optical lattice like this. And we clearly observe the STO signal along the strong link in a 1D optical lattice. This. And this is a case of 2D square lattice. Again, we clearly observe the STO signal for the strong link within a 2D layer. And in the case of weak link between the 1D layer, 1D chains, or 2D layers, we didn't observe the clear STO signal like this. Yeah, this is consistent. And finally, we successfully observed the spin STO signal for completely isotropic 3D cubic lattice configuration like this. And rough estimate of the temperature of the atoms, in this 3D cubic lattice gives about 40% of the hopping energy. So this is really cold. Yeah, of course, we need very sophisticated theoretical calculation to determine the temperature of the atoms, but we apply atomic limit approximation to estimate this temperature. I think it's not so different from the real temperature. Okay. And observed spin correlation is plotted as a function of the number of nearest neighbors with weak rings. Okay, and the dimerized lattice has 5 weak rings per side, and 1D lattice have 4 weak rings per side, and this corresponds to the 2D square lattice, and 3D isotropic cubic lattice has no weak ring. And here you can clearly observe that higher spin correlation is achieved for larger number of weak rings. This behavior can be understood as the larger capacity of entropy for weak rings, because it has a very small exchange energy, so it can, it has a larger capacity of entropy. And similar behavior is also observed for the case of SU2. And we also recently studied the novel quantum magnetism of SU6 Fermi gas by loading them into this isolated bracket lattice like this. Here, the inter-bracket hopping is much smaller than the intra-bracket hopping, like this. And interestingly, the ground state of the 4 spin in bracket lattice configuration is the SU4 singlet state, expressed like this by using the fermion creation operator, C dagger. Here, IJKL represents the site index, A, B, C, D, and 1, 2, 3, 4 represent the spin index of SU6 Fermi gas. And our STO measurements show that there are almost perfect spin correlation along A, B, C, D, and AC, BD. So this is consistent with the successful formation of SU4 singlet state, because this SU4 singlet state can be also expressed like this as a superposition of the SU2 type singlet state along A, B, C, D, or AC, BD. So these results are consistent with the formation of SU4 singlet state. The SU4 singlet state is a 4-body entangled state. It's a novel entangled state for the atoms in optical lattice. And we think that it is interesting to study the stability of the SU4 singlet state after suddenly we increase the inter-bracket hopping and turn into the standard square lattice, where the novel Néel order of dimers is predicted theoretically. Okay. And this experiment, Quincy experiment, is now underway in our lab. And finally, I would like to make an interesting analogy with the SU4 singlet state. SU4 singlet state itself is already realized in the nuclear physics. It is an alpha particle, which is a nucleus of the helium-4 atom. And it consists of the 2 protons and 2 neutrons. And protons and neutron has a nuclear spin 1/2. So it has a spin up and spin down. And protons or neutrons are also considered as a isospin up and down. So the alpha particle can be considered as a SU4 system consisted of nuclear spin 1/2 and isospin 1/2. And yeah, I don't know. We can do some interesting physics related with the alpha particle, but yeah, just an interesting analogy. Okay. For detecting the short-range spin correlation, STO method is really helpful. It's useful. But for detecting the long-range spin correlation, we need a quantum gas microscope for SU4 Fermi gas. In our previous experiment, we developed the quantum gas microscope for bosonic isotope of ytterbium-174 with the fluorescence imaging method and also Faraday imaging method. This Faraday imaging method has inherent nuclear spin dependence, so we plan to apply this method for the study of SU and fermions in a 2D optical lattice. Okay, and I would like to switch to the third part of my talk. It's about the two-orbital quantum simulator. Okay, another unique feature of the two-electron atoms is the existence of the stable electronic state of a single lattice 0 and triple P0. Interestingly, there is a spin exchange interaction between the atoms of these 2 electronic states. Therefore, it is a nice system to study the spin orbital physics, such as a Kondo effect. In a Kondo effect, localized spin in one orbital strongly modify the quantum transport of the particle in another orbital by forming the spin singlet state. In a solid state system, the Kondo effect manifests itself as an increase of the resistance by lowering the temperature like this. But in our cold atom system, we can study the Kondo effect, especially its dynamics, in a very controllable way. That is our motivation. But we should be careful that spin exchange interaction should be antiferromagnetic for the study of a Kondo effect, because spin singlet states should be formed to modify the quantum transport. This spin exchange interaction is proportional to the difference of the scattering rings for 2 different collision channels of Eg plus and Eg minus. And it was measured for 2 atomic species of ytterbium-173 and strontium-87. And these are found to be ferromagnetic. So it is not straightforward to apply these atomic species for the study of a Kondo effect. But recently, novel scheme of the confinement-induced resonance was demonstrated to change the behavior of a spin exchange interaction. But still, there is an atom loss associated with this confinement-induced resonance. So, yeah, still it's not straightforward. But in our approach, we explore a different possibility of ytterbium-171 as a possible Kondo simulator. For ytterbium-171, only the ground state scattering rings is known to be very small. And interorbital scattering rings are not known. Okay? To determine these interorbital scattering rings, we performed high-resolution laser spectroscopy of ytterbium 171 in an optical lattice. And details described in this our recent paper. And from these measurements, we could determine the interorbital scattering length for ytterbium 171. And this is the result. And importantly, the difference is negative. So we found that the ytterbium 171 has a required antiferromagnetic spin exchange interaction. Therefore, it is good for quantum simulation of the Kondo effect. Okay, and to study the Kondo effect, we also need a two-orbital system with localized triplet P0 and itinerant singlet 0. We need to construct this novel optical lattice. And this was realized in the following way. First, we apply a 2D optical lattice with a magic wavelength of 759 nanometer. Therefore, the optical lattice potential is deep both for triplet P0 and singlet 0. So in this way, we could prepare the 1D tubes like this. And in addition, we apply a optical lattice along the 1D tube at the wavelength of 650 nanometer. At this wavelength, the optical lattice potential is only deep for triplet P0 and almost no effect for the ground state. In this way, we could prepare the localized triplet P0 and itinerant singlet 0 in one dimension. Okay? We performed two measurements using this novel optical lattice. And the first is the measurement of the dipole oscillation. And in the absence of the triplet P0 atoms, we clearly observe the dipole oscillation for the atoms in the ground state singlet 0. And oscillation frequency is consistent with the trapping frequency along the 1D tube. Yeah? And in the presence of the localized triplet P0 atoms, we observe the strong damping of the dipole oscillation. Okay? And as far as we know, this is the first example of the suppression of the dipole oscillation by localized impurities. Okay. And second measurement is about the spin exchange process. For this purpose, we applied an optical Stern-Gerlach imaging method to separately image the spin up and down in the ground state. And with this method, we clearly image spin up and down separately, as shown here. Okay? And there are almost equal population in the ground state, spin up and down. To induce the spin exchange process, we transfer spin down atoms in the ground state into a triplet P0 state. And then we have a large spin imbalance in the ground state, as shown in this Stern-Gerlach image. After some hold time, spin exchange process should occur like this, and then initially prepared spin imbalance can be reduced. This was actually observed in our experiment like this. After 70 milliseconds, the spin imbalance is greatly reduced. And here we plot the spin up and down, number of spin up and down as a function of the hold time. We clearly observe the spin exchange process in this way. And atoms are depolarized with a time constant of about 11 milliseconds in this system. And this successful observation of the spin exchange process in a two-orbital ytterbium 171 is an important first step for the study of a Kondo effect. Yeah. And through the collaboration with theoretical collaborators, we are now trying to understand these observed behavior quantitatively. Okay, and I don't have enough time for the discussion of the our experimental efforts on a dissipative Hubbard model. Here we reveal the novel role of dissipation in stabilizing the quantum many-body state. And I summarize the result in one slide. We introduce the engineered two-body dissipation in the ground state of singulated zero state by the application of the photoassociation laser beam. And also, we use the intrinsic two-body dissipation inherent in the metastable state of a triple P2 state. And with these two experiments, we reveal the delay of a melting of the motor insulator state and suppression of the phase coherence of a superfluid due to the dissipation. Okay. This is a summary of my talk. I reported on the successful observation of the quantum magnetism of SUN fermions. And also, I talked about our efforts for two-orbital quantum simulator with ytterbium 171 Fermi gas. I don't have enough time to talk about this topic. Okay. And finally, I'd like to introduce our group members. These people are working very hard. And in addition, we have a nice collaboration with Professor Yamamoto and Professor Danshita and Dr. Goto for theoretical analysis of our experiment. Okay, thank you very much for your attention.